Hello. For this next section, we're going to talk about data representation. In the section before, we looked at all the different tools that are available to do a quick inspection. However, if you need to address issues that are not covered by those tools, you might have to create a visualization tool yourself, and then you need to figure out how to translate your data into images and displays on the screen. So, for the most part, most are now have an intuition of what it means just to put points on the screen, do a scatter plot. That's a pretty easy thing to do. And of course, you could actually attach all these points with a line to actually signify that there's some continuity to this. Now, also, you could also display the same number of points as a bar chart, in which you're actually putting more weight to what each of these points are as far as how advanced they are in the second variable. What this means is that even a simple plot between points or a line plot or a bar chart, they already start telling a slightly different story. You can add complexity to this simply by overlaying different plots together. Now you're actually making several points at the same time. Similarly, if we look at an example that Edward Tufte showed in 2008, we actually have here a series of plots that are actually both showing different elements in pollution in the LA basin at different times. This is what he called small multiples. But basically, by having a series of plots laid out in a grid, you actually both convey a sense of motion as well as a way to compare different things. So complexity can come simply from laying out things differently, from putting things next to each other. This is the concept of layering, which we'll talk a little more in the next following area. Now, another way to add complexity is by making the elements that you're showing more complex. So instead of drawing a point in space, you can actually draw a glyph. Imagine you have a data point that has 5 different variables, and for each of these variables you have a range that you normalize from 0 to 1. You can actually show the value, the normalized value for each of these variables as different points in an axis and then connect them to actually make a glyph, to actually make an image that signifies a particular data value. Now you can actually use this as an element that you show in a scatter plot by having many of these star glyphs in space, or you can even superimpose them, layer them on top of each other to show more of a sense of motion or depth. Here, each different data record is being shown by one of these connections, by a different star glyph overlaid on top of each other to create what we call a star plot. Another way to show complexity is what now we know as box plots, where instead of showing a series of points like you have on the right, you actually show the limits of what this data is by creating a line with little whiskers on top and bottom that actually show the maximum and the minimum value of a range of points. And then you actually show where the median value is by creating a little line that goes horizontal in this case, and then showing how far you have to go to reach 25% of the data in each direction. So this series of points right here that we have right here, which is a very populated set of points, can be simplified by creating a more complex visualization with this box plot right here on the right, which actually shows kind of like the curve of distribution for these data points by simply creating this small representation. In fact, there is lots of different ways of visualizing data. There's different plot possibilities. Here is an example of how to come up with different ways of visualizing your data depending on the number of variables you have, whether you want to compare them or you just want to measure each of the information. There was a plot developed by Andrew Avell, and it's a good starting point for understanding different possibilities. Well, it's definitely not all the different possibilities that are out there. But now we can start talking about, okay, what does it mean to choose one of these plots and really kind of push it forward to actually show complex data? That's where we start talking about layering. the ability to put information and layer more complex information on top of it. Now, there's two ways to layer data. One is to actually just put different plots on top of each other, so that would be more of a layout layering, or you can actually show more complex information per each data point, per each data item. Edward Tufte is a statistician from Princeton that did an amazing job of curating some of the best visualization that has been out there for the last 200 years. And he's very much shown that it's possible to show highly efficient, highly effective plots by simply being very mindful of how you present your information. Tufte, in many ways, has become the parent of modern scientific visualization. And for that, he's very well known for showing this one plot of Napoleon's attack on Russia. And what he's showing, and what Maynard did in 1812, was actually show this plot that actually shows the movement of army from France going into Moscow, which is represented by this sepia line right here, where the width is actually the number of troops. Notice that as it advances in Moscow, he started to lose people, which the width actually becomes smaller and smaller and smaller, while eventually reaching Moscow, being defeated, and having to retreat. So this one plot shows movement of these troops across time. It shows how many troops are at any point in time. It overlays it on top of geography, so you can see the rivers that it crossed. You can see very clearly on its retreat right here, it crossed this one river, and there was a big, it's already small number of troops got even more diminished during the cross of this river. And on top of that, he actually physically layers one plot on top of another plot, actually putting the different temperatures in the year and linking them through these lines. This is a very amazing example that's actually showing in a single visualization. In a single graphic, it shows this dynamic movement of troops, of geography, of temperature, and it is very efficient in telling a story. In fact, we can really say that data visualization really resides in this environment between science and visual communication. For scientific visualization, for the most part, we're very concerned in making sure that we're true to the science. But in order to do so, we really have to be productive and effective at presenting the data. So there's many concepts that we do need to use, and those come from graphic design. And those are both applicable to the data representation itself as well as the visual layout. So for that, let's talk a little bit about the different graphic design elements that we have available to us. The more clear ones is we have the use of lines, the use of shapes, but we also have the use of size. We can use the space around an element, and of course you can use color and the value, how light or dark something is. We can combine even these things to actually create more complex elements like texture. If you're representing data, imagine a scatter plot, you can have different points on the screen which are represented by their position, already telling you information, but you can actually scale them in different ways to actually show an additional variable. You can orient them to even show more interesting information. You can vary their shape. You can add distinctive points. You can tie information together. You can add whiskers like we saw with the box plots. You can make more complex glyphs like we saw with the star glyphs. And of course, you can use color, which you can actually vary both the hue, saturation, as well as the luminosity. You can combine it with other elements to actually create texture. Finally, in an interactive screen, you can even add motion to it. You can add simple vibrations, you can add rotations, you can even add deformations that could actually map different variables to these movements. Now notice that while you have quite a number of variables that you can map data into, you really have to drive yourself by the different principles on how to make sure that the data is not overwhelming and in fact it becomes understandable. So for that, it's important to actually know a little bit about graphic design principles. These include the idea of dominance, that for a visual representation to be successful, it is best to have an element that's stronger than the others. That means something you can pay attention to first before you start diving into the other layers of information. Notice that can be done by color, that can be done by location, by depth. In fact, the way you can be really good or strong about whether something is tied together or is different is by contrast. You can do that by contrast of shape, you can do that by contrast of hue, contrast of value. Contrary, if you want to say something is very closely tied together, it doesn't have to be the same shape. You can actually use any kind of repetition. You can use an outline, and if the outline is repeated, then automatically you're tying information together. So that can be a way to actually present information that is actually meant to be seen as together. Notice that alignment is also a way to present data. If you want to say that some points belong in a category by themselves, you can just align them in one side and a different category, align them on a different side. Notice the same is true that if for some reason some points happen to form a line, a viewer might actually take those to actually having some kind of connection between them, even though if you didn't mean it. Same true is proximity. Things that are closer together, regardless of shape or color, can actually be seen as belonging together, as having some information that makes them common. And that brings the whole idea to the idea of balance. The more balance you have in your layout, the more it's going to feel like things are laid out correctly. If you're heavy on one side and lighter on the other side, you're actually giving an idea that there's something interesting about that maybe all points are meant to be together and everything else is an outlier, for instance. All these graphic design principles are applicable to the data encoding and the data presentation. So for instance, let's take a look at an example from the GE World of Records, in which they actually presented all the records from the past Olympics, and they actually use a point representation. So the first thing is they use this kind of bar chart look, but then each of these stacked bars was actually a set of points, which were actually interactive. You could put your mouse over a point and you could get information of specific records that were done. Now, the other thing that you're actually doing is you're actually also using color to actually create groups of things. In this case, there are different categories of sports. Notice that in the same bar chart, just by looking at the color, you're already grouping elements, and you can already start drawing conclusions. You can already start telling a story about the different sports and when their records are more likely done. By adding interaction to it, you can switch your whole layout simply by switching position, and you can present a different set of information. For in this case, you just create clusters of the different points being represented, and now you can make a different conclusion about the number of records in swimming versus the number of records in cycling, for instance. You can do one more change and change the position, and even change the visual composition of it to actually create how long a record has stood for. So you're adding an element of time and duration by simply creating a different representation rather than a dot, actually elongating it and showing it how long it lasted in the axis of time. Here is a different representation that we did here at Caltech as part of the PISA project, in which we're actually showing a campaign of different computations done across 6 different machines in the national labs. Now, we launched computations that were actually linked to each other, and we wanted to see how efficient we were with each computations. So here we isolate each of the jobs and a representation that actually show how many cores we used in each of these jobs, how big was the job, and then how efficient it was. For scientific computation, a 10% of peak success is almost the top you can ever achieve. So we normalized the efficiency to actually be an internal circle that went from 0 to 10. So in this case, you can see that there's a job here that performed at almost 5%. So you see an internal circle showing 5%, only about half the radius, half the diameter of the outer circle. In this case, this job actually used 64 cores. And here we have a different job that they used 4 cores for a different machine and actually used about almost 7 to 8% of efficiency. Notice in this case, we're not only using position, by using color to signify different machines. We actually changing the shape by overlaying different shapes and even attaching different whiskers or accessories to these things to actually show the number of cores. So we're creating these complex representations that actually allows us to show more information. In this case, you can see clearly that efficiency is the element that we are trying to show the most.